last time we did projective measurements, and I summarized that up here. Let me walk you back to the postulates of quantum mechanics, which I've written down again. And sort of in summary form, hopefully you should be able to do the same by now. So the first postulate being that quantum states are elements of a Hilbert space. For us in finite dimensions, that means a vector space with an inner product. And valid quantum states have norm 1. The second postulate says that the evolution of quantum states is unitary. So psi is the initial state, evolves to some new state psi prime at a later time. That evolution will always be unitary. U dagger U is equal to the identity. The third postulate is the measurement postulate. This one says that a measurement is described by a collection of operators, capital M sub little m, such that the completeness relation is true. So when you sum over all of them, dagger you get identity. And then there's two equations you need to remember. One, what is the probability of getting outcome m? That's given by this. So the inner product psi, dagger, psi. And then the second one is what happens after the measurement. So supposing we get measurement outcome m, we'll say this, in several ways. M was measured, little m was measured. We got the measurement outcome little m, or we measured capital M sub m. In that case, the quantum state immediately after the measurement transforms to applied to psi, and then you just need to remember to renormalize it. Square root of the probability P of m. The last postulate is that for composite quantum states, the composite state is the tensor product of individual states. So hopefully you remember the postulates, and we started saying more about them. So postulate 4 led us to entanglement, very unique quantum thing. We're going to say some more about entanglement, maybe by the end of today, but definitely in the next session. And then we started saying more about the third postulate, that being of the measurements. So we covered chapter 2.2.5 on projective measurements. And all this is a special case of the third postulate, where the measurement operators are Hermitian orthogonal projectors. In this case, we just use the notation P sub m to remind us that we have projectors. But it's the same thing. Gets relabeled to PM. And then in this case, from this, you can clearly show from the postulate the probability of measurement outcome m is you just need one PM in the middle because of the orthogonality condition. And then the state after the measurement gets updated correspondingly. That's just a relabeling to P sub m. Furthermore, we showed that for an observable, which we defined as a Hermitian operator, since it's Hermitian, it's normal, and it has a spectral decomposition, which we wrote in the following way, sum over m, P sub m. In this case, we proved that the average value, the expectation value of m, is equal to psi m psi. That's where we left off, and then I just wanted to write down the standard deviation formally. We saw it in Heisenberg's uncertainty principle. But the definition of this is the expected value of m minus the expected value of m quantity squared, which you can easily work out with algebra to be equal to this. So if you're ever asked to compute standard deviation, you just have to compute two expectation values. The first one being of m squared, the second one being of m, and then you square it.